Hello and welcome to this 11th set of problems on arithmetic progression, geometric progression, and harmonic progression. So, in this set, we will solve problem number 101 to 110. And as always, I'll say that when I'm stating the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. So, without further ado, let's get started. Problem 101 says that if Sn be the sum of infinite GPs whose first term is n and the common ratio is 1 by n plus 1, find the limit n tending to infinity S1 Sn plus S2 Sn minus 1 and so on up to Sn S1 divided by S1 square plus S2 square up to Sn square. So S1 would be 1 by 1 minus 1 by 2 because first term is n. Here the value of n is 1. So first term would be 1 and common ratio would be 1 by n plus 1, that is 1 by 1 plus 1 or 1 by 2. So S1 would be 2. For S2 first term would be 2 and common ratio would be 1 by 3. So S2 would be 3. We proceed similarly to find out Sn, which is n by 1 minus 1 by n plus 1 or n plus 1. So the general term of numerator can be written as Ti is equal to Si Sn minus I plus 1. So if you substitute I is equal to 1, you get S1 Sn and so on. So we write the values of Si and Sn minus I plus 1, which is I plus 1 and n minus I plus 2. We multiply this to get n plus 1 into I minus I square plus n plus 1. So sum for numerator would be sum of n ti's, that is where I varies from 1 to n. So we apply the formula and we get the result as n into n plus 1 whole square by 2 minus n into n plus 1 into 2n plus 1 is 6 plus n into n plus 1. And for sum of denominator, we add 1 square and minus 1 square to the series of 2 square plus n plus 1 whole square. So it comes out as n plus 1 into n plus 2 into 2n plus 3 by 6 minus 1. Now, for the last step, you will have to have the concept of limits. So if you see the sum for numerator, this term contains a power of n cube and this contains a power of 2n cube. So if we take LCM, and here it is denominator is 2, here it is 6. So this n cube will become 3n cube and 2n cube will remain same. So upon subtraction it will give n cube, that is with coefficient 1. And here if you see, if you multiply all this, you will get 2n cube. So if we divide both numerator and denominator with n cube, we will have 1 by 2 and other terms will contain powers with n in denominator. So when n will tend to infinity, other terms will become 0, leaving the ratio as 1 by 2. Problem 102 says that the sum of the terms of an infinitely decreasing GP is equal to the greatest value of the function x is equal to x cube plus 3x minus 9 on the interval minus 5 comma 3. Note that this is a closed interval, that is, it includes both minus 5 and 3 as values. And the difference between the first and second terms is f dash 0. Prove that the common ratio of the progression is 2 by 3. So f dash x on differentiation will yield 3x square plus 3, which will have imaginary roots. That means there is no local maxima. Now we observe that 3x square plus 3 is positive for all values of x in the given interval, which means that fx is monotonically increasing in that interval, which further implies that maximum value will be at x is equal to 3. So f of 3 is 27, which will be the sum of the geometric progression. Now we let a to be the first term and r to be the common ratio. Then the difference of first and second term is f dash 0, that is 3. How it becomes 3 is in f dash x you substitute x is equal to 0, 3x square will become 0 and 3 will remain. This is 3. Now the sum would be a by 1 minus r, which is 27, which is what we have obtained here. Now when you solve this and this, you get r is equal to 2 by 3 and minus 4 by 3. Now series is decreasing, so r would be 2 by 3. Problem 103 says that find the sum of the series 5 by 13 plus 55 by 13 square plus 555 by 13 cube and so on up to infinity. So we write the series and let the sum to be s. Now we take out 5 common from the numerator. Here we have taken out 5. So what will remain is 1, 11, 111. We multiply and divide by 9. So we get 9 over here. And this is 9, this is 99, and this is 999, and so on. So we can rewrite this in form of two geometric progressions. One would be 10 by 13, 10 square by 13 square plus 10 cube by 13 cube up to infinity. And the second would be these minus 1s, that is minus 1 by 13, minus 1 by 13 square, and so on. Now both have a common ratio less than 1. This is 10 by 13 and this is 1 by 13. So we simply apply the formula of sum of infinite terms and we obtain the end result as 65 by 36. Problem 104 says that if e to the power sine square x plus sine 4x sine to the power 6x and to infinity, now this whole is multiplied with log of 2 with base e, there should be parenthesis for more clarity. Satisfy the equation x square minus 9x plus 8 is equal to 0. Find the value of cos x by cos x plus sin x, where x lies between 0 and pi by 2. Now it involves a bit of logarithm knowledge. In this case, we swap 2 and e here, and the sum of series would be sin square by 1 minus sin square x, and the log will become log of e with base e. That means it is equal to 2 to the power tan square x. Now the given equation is x square minus 9x plus 8 is equal to 0. That gives us x is equal to 1 as root, one of the roots. 1 is 2 to the power 0 and the second root is x is equal to 8, that is 2 to the power 3. Now if we take 2 to the power 0 and we equate with 2 to the power tan square x, then tan square x will be 0, that is x is equal to 0, but x is greater than 0. So we take 2 to the power 3, that means tan x would be square root of 3, which means x is equal to pi by 3 in the range 0 to pi by 2. Once we have found x as pi by 3, we simply substitute the values in cos x by cos x plus sin x to get the result as 1 by 1 plus square root of 3. Problem 105 says that if x lies between minus pi by 2 and pi by 2, the sum to infinite number of terms of series cos x plus 2 by 3 cos x sin square x plus 4 by 9 cos x sin x to the power 4x is finite, then show that x lies in the set minus pi by 2 and pi by 2. So we find the sum as first term, which is cos x, divided by 1 minus common ratio, which is 2 by 3 sin square x. So this is equal to 3 cos x by 3 minus 2 sin square x. Now if you observe carefully, this cos x will not be 0 in the range open interval minus pi by 2 and pi by 2. And sin square will vary with a value of minus 1 to plus 1. That is sin square x will be 1 to 0, that is 0 to 1. So the value of denominator will be finite, that is it will be between 1 and 3. So this is between 1 and 3 and numerator would be between 0 and 0, but 0 will be excluded. So it will be a non-zero value basically because the interval is open, so the angles pi by 2 and minus pi by 2 will not be considered. But greater than minus pi by 2 and less than pi by 2 will be considered. So our numerator is finite, our denominator is finite. This step is actually not needed. So this would be finite for all x in minus pi by 2 and pi by 2. Problem 106 says that suppose x lies between 0 and pi. This is an open interval because it is greater than not equal to and the expression e to the power 1 plus modulus of cos x plus cos square x plus mod of cos cube x to infinity whole multiplied with log of 4 with basis satisfy the quadratic equation y square minus 20y plus 64 is equal to 0. Then find the value of x. So this is similar to the problem which we have solved just now with the series sin square x plus sin to power 4x. So similarly, here we change the e with 4. So it becomes 4 to the power 1 by 1 minus mod of cos x log of e with base e, which is equal to 4 to the power 1 by 1 minus mod of cos x. Now y square minus 20y plus 64 is equal to 0 will yield two roots. That is y is equal to 4 and 16. So the power when we compare here 1 minus 1 by 1 minus cos modulus of cos x will be equal to 1 or 2. Now if it is 1, then mod of cos x will be 0. That means x is not an element of 0 comma pi. Okay. Now if yeah, mod of cos x is 0 because no, hang on, let me see this. Yeah, mod of cos x is 0. Then x does not belong inside 0 comma pi because it will be pi by 2 x modulus cos x is equal to 0 means x is equal to pi by 2. Hang on, let me check this. So this is 1. Okay. No, in this case also it will belong to the open interval because x would be pi by 2. So for x is equal to pi by 2 cos x will be 0. So it will belong to this open set. So 1 minus mod of cos x, if we consider 2, then it will become 1 by 2. The root, if we consider 2, then it will become 1 by 2. So x would be n pi plus pi by 3, where n belongs to the set of integers. Problem number 107 says that an AP and a GP with positive terms have the same number of terms, and their first terms as well as the last terms are equal, so that the sum of AP is greater than or equal to the sum of the GP. So here we let A to be the first term and B to be the last term, and N be the number of terms in both the progressions. Then common difference of AP would be B minus A by N minus 1, and common ratio of GP would be B by A whole to the power N minus 1. Now we let S to be the sum of N terms of AP and S prime the corresponding sum of GP. So clearly sum for AP would be N by 2 into first term plus last term, that is A plus B. Now S prime would be A into 1 plus R square up to R to the power 2 R to the power N minus 1. We reverse the terms and write S prime again. It is A into R to the power N minus 1 plus R to the power N minus 2 up to 1. So S prime would be A by 2 into 1 plus R to the power N minus 1 plus R to the power N minus 2 and so on. So what we will try to prove that general term is actually less than some specific term, that is R to the power N minus 1 plus 1. Once we have established this, the sequence will be simpler to handle. So we take R to the power k plus R to the power N minus k minus 1, which is a general term, minus R to the power N minus 1 plus 1. We rearrange and we rewrite this. We take out R to the power k minus 1 common, and we have then R to the power k minus 1 multiplied with 1 minus R to the power minus N minus k minus 1. Now this will be less than or equal to 0. The reason is, if R is less than 1, then this term would be negative and this would be positive. If R is 1, then both will be 0. If R is greater than 1, then this term would be negative and this term would be positive. So the whole is less than 0. Now once we have established this, we can rewrite this as A into n by 2 multiplied with 1 plus R to the power n minus 1. Because from here, R to the power n plus 1 will be greater than each term or equal to that. So once we have written this, we can rewrite R to the power n minus 1 as P by A, and then we add, we get A plus B by 2 into n, that is S. And that's why we can say that sum of arithmetic progression is greater than equal to sum of corresponding geometric progression. Problem 108 says that given a GP and AP of positive terms a, comma a1, comma a2 up to an and so on, and b, comma b1, comma b2 up to bn and so on respectively, with the common ratio of the GP being different from 1. Prove that there exists an x in set of real numbers greater than 0 such that log of an with base x minus bn is equal to log of a with base x minus b, where n belongs to set of natural numbers. Now we have a1, a2, a3 are in GP. So if you take log of those, then it will form an AP. And the common difference of this AP is D1. We have let it to be D1. So we can write that log of n is equal to log of a plus n D1. Now if D is the common difference of AP, then Bn is equal to B plus ND. So from here we get ND1 is equal to log of n minus log of a. From here we get nd is equal to b n minus b, and we divide them to obtain this expression. Now we let log x is equal to d1 by d for some fixed positive real number x. Once we have taken this, the expression becomes log of n minus log of a by bn minus b is equal to log of x. That means we take out bn minus b over here, so it becomes log of n minus log of a by log of x, which implies it is equal to log of n by a with base x. Once we have this, we can write this as log of n by x minus log of a by x is equal to bn minus b. That is log of n with base x minus bn is equal to log of a with base x minus b. Problem number 109 says that if the m plus 1th, n plus 1th and r plus 1th term of an AP are in GP and m and r in HP, show that the ratio of the first term to the common difference of the AP is minus n by 2. So we are given that a plus md, a plus nd, a plus rd are in GP, where a is the first term and d is the common difference of AP. So we can write that square of middle term is equal to product of first and third term. So we solve this to obtain d by a is equal to m plus r minus 2n by n square minus mr. Now we know that m and r are in HP, so we can write that middle term is equal to twice of product of extremes and sum of extremes. That is m plus r will become 2mr by n. Now we substitute this value of m plus r in this, and then we obtain a by d is equal to minus n by 2 by simplification. Problem number 110 says that if A, B, C are in GP, A minus B, comma C minus A, comma B minus C are in HP, then show that A plus 4B plus C is equal to 0. So we let R to be the common ratio of the GP, then B is equal to AR, C is equal to AR square. Now we are given that A minus B, comma C minus A, comma B minus C are in HP. So we write the formula for mean of harmonic progression. We get C minus A is equal to 2 into A minus B into B minus C by A minus B plus B minus C. Now we can simply see that it is a matter of solving this expression to obtain 1 plus 4r plus r square is equal to 0. Then you multiply this with A and you obtain A plus 4b plus C is equal to 0. With this, we come to the end of 11th set of the problems, and I hope you have found it useful, and if so, then please subscribe to the channel and like the video so that it can reach to more people, and it also motivates me to make more videos. If you have a question, a comment or a suggestion, write into comment box and let me know your thoughts on this. Thanks a lot for watching. Bye.